So ones and zeros are not very useful if we can't combine them into some sort of pattern. So in this topic, what we're going to do is we're going to discuss binary. This is the combining of the ones and zeros. So when we do this, when we combine ones and zeros, it gives us a new system, which is a base 2 system, right? There are 2 digits. That's where the base 2 comes from. Just like in our counting system, we had 10, right? 10 fingers, 10 toes. We counted from 0 up to 9, and that gave us 10 digits for base 10. This one is a base 2, and it's called a binary number system. So let's take a look at what it's comprised of. If you remember back, we looked at placeholders or positional notation, right? Each one of these columns, we had a base 10 to it, and then it was raised to a power. So each position here in base 2 has the same principle. You see that it starts over on the right with 2 to the power of 0. Then it goes the power of 1, power of 2, power of 3 over and continues on. So right here, I'm just showing to the power of 7, but it can continue on depending upon the size of the computer and how much the computer can handle. So if you break that down, what you need to look at then is compute that over. Each one of those positions gives you a value. So at 2 to the power of 0, that's the ones position, right? So you would say, what? If I had a 1 in that position, what would it be? It would be a 1. So it would be 2 to the power of 0 is 1. 2 to the power of 1 is 2. So if I had a 1 in that position, it would be 1 times 2, which would be 2. And then you add each one of these columns together, and we're going to go through that. So it's nice and clear in your mind. Well, let's walk through, and we're going to look at each one of the values as we go through this. I just want to make sure that you understand what positional notation is. So if I'm going to go in each one of these boxes and I put a 1 in each box, what's it going to equate to? 2 to the power of 0, we just talked about, that will be a 1. 2 to the power of 1 will be a 2. Can you guess what 2 to the power of 2 is? 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. 2 to the power of 5 is 32. 2 to the power of 6 is 64. 2 to the power of 7 is 128, and then it just continues on. Do you see the pattern? Let's do it with zeros. Well, this should be easy. It just is 0, 0, 0, 0, 0. See how our base 2 system, it's either going to be 0 in that position, or it's going to be to the base 2. Pretty simple stuff. All right. What is the range of numbers when we're using 2 to the power of 0 to 2 to the power of 7? What's going to be the range of numbers when we combine all those individual bits together? Now let's lay it out. Maybe it's easier if we just lay it out. So I've got a range. I've got x to x. Let's figure out what the x's are going to be. So if I put all zeros in there, obviously it's going to be 0, right? So we know that the minimum number here in our range, our set of numbers, is 0. What if I put all ones in there? So here's all ones. What's that going to be equal to? Stop this video and compute it out for yourself. I want to see if you know how to take each of these positional numbers and compute out that total range. What's the maximum number here in our number set? We'll go from 0 to what? If you don't remember, you need to take each of these columns. So at 2 to the power of 7, you take that value and you add it to the equivalent value in each one of these columns, and it comes up with a number for you. Once you get it, go ahead and start the video back up again. Okay, so if you were successful at it, then you would find that the total range, so our set of numbers goes from 0 to 255. And what's that mean? It means we have 256 different values that we can represent with these 8 bits. That makes sense to you? By combining the pattern of ones and zeros for just these 8 individual bits, we can come up with 256 different values. That's the power of combining ones and zeros into a pattern. And just to help you understand each one of these positions, we'll go ahead and fill this out for you. So until you get to know these, you can just go ahead and fill these out. You can put it times 1, times 2, times 4, all the way over. That way each one of your notational positions makes sense to you. All that you have to do at 2 to the power of 6 is take the 1 times 164, and what's it going to equal? Well, that's pretty simple. That's 64. And then just add all these columns together. That gives you your total. Okay, so let's do some problem sets. Let's help you to break this down, okay? We're going to convert a decimal to binary. We're going to do it in 2 different problem sets to give you some practice here. All right, let's do this first one. Ready? 21 makes sense. In one of our last topics, we talked about 21 clocks. So let's take 21. Let's figure out how the number representation of 2, 1, how does that break down into binary? What you want to do is start the left-hand side. And you're going to look at that and you're going to say, how many 128s are in 21? You're going to say, well, there's none. Nope, there's no 64s. Nope, there's no 32s. Yeah, 16 can go into 21, right? So I've got one of those. How many do I have left over? 21 minus 16, you got 5, right? All right, so 5 is less than 8. So nope, I don't have any 8s. Yes, I have a 4. So now I've got 16 plus 4 is 20. That gives me 1 left, right? So nope, it's not a 2. And yes, it's a 1. Do you remember that from grammar school? How you break down numbers? No, you probably didn't do it in binary, unless you went to an amazing school that taught you binary. But you know positional notation from decimal 10 and how we break down numbers. Let's do one more. 33. All right, let's do this one again. How many 128s are in 33? None. Nope, there's no 64s. Yes, there is one 32. Okay, so that leaves me with 1 left over, right? So yes, I have one of those. That would mean, no, I don't have any 16s. I don't have any 8s. I don't have any 4s. I don't have any 2s. Yes, I have a 1. Okay, that's my binary representation of 33. Let's go the other way. Let's convert from binary to decimal. So here is my binary. I'm going to go ahead and give you the columns. These are the values then for each one of these positions. So it doesn't matter which way you want to start, right or left. Doesn't matter. This time, let's start on the right. So 2 to the power of 0 with 0 is what? 0. So really all that you want to be concerned with are the ones with the 1 in that column. Okay. So the next one, 2 to the power of 1. I have a 1 in that column. And we can see, if you want to look at your cheat sheet there, it'd be times 2. So therefore, let's bring a 2 down. I have 1 in the 2 to the power of 2, and that value would be a 4, correct? So I would take 1 times 4 is 4. Moving along, I can see my next one in this pattern is in the 2 to the power of 6. So 1 times 64 is 64. Then I want to add 64 plus 4 plus 2, and that gives me 70. Now, if this does not make sense to you, you need to stop right now, because the series of topics and the rest of this lesson are all predicated upon you understanding this right here. So stop, take some time, make sure that you understand it, and then you can move on. Okay. Let's do terminology. Well, this should look familiar. This is your binary notation. One single digital digit or position here is a bit. It's our binary digit, and it's going to be a bit. Now, the one that's on the right, the furthest bit on the right, if you look at the pattern, look across, what do you see? What would be a name that you'd want to give to 2 to the power of 0, which is a 1? So if I'm looking at this, I can say, okay, what's the pattern that I see here? Remember, we're going to be talking a lot about noticing patterns. You need to think about what type of pattern that you're seeing. So what is it? You can see that 2 to the power of 0 is less than 2 to the power of 1. It's less than 2 to the power of 2. It's the smallest one, isn't it? It's the least significant digit. That's what it is. So if you see that term, LSB, it's the least significant bit. Sometimes you'll see it as least significant digit also. But here we're going to call it LSB, least significant bit. If you see that term, now you know what that means. It's referring to the smallest value, the smallest positional notation column in the pattern, in the series. Okay? So let's go to the other way. If I look at that 2 to the power of 7 in this pattern, and what I just brought up to you with that one's the least significant bit, what would be 2 to the power of 7? Well, obviously it has the greatest value of each of these columns, each of these positions, right? So why don't we call that one the most significant bit? If you're dealing in decimal, that would be most significant digit. Here it's most significant bit in binary. Okay, let's go ahead. Now, if I take 8 bits, what are 8 bits? What would you term that to be? That's 1 byte. And you know bytes, right? All the memory that we deal with, the size of our hard drives, the size of RAM, is all expressed in a proportion of bytes. How many bytes does something have? So bytes are very important to a computer. In talking about a bit and a byte, you need to know those. Let's go a little bit further. This is what? It's 1 byte. See that? There are 8 bits. That's our least significant. Now I can say 8 bits, that's 1 byte. Let's put one more on there. Okay. Now I have another 8 bits. What position on here is the most significant bit? Which one now? Last time it was 2 to the power of 7. Is it the case this time in this particular pattern? You should be shaking your head no. It's 2 to the power of 15. You have to look at the pattern that you have. So if I'm given 2 bytes, then the one on the furthest left, which is 2 to the power of 15, is going to be my most significant digit. So therefore, that most significant digit is going to move. It's going to be dependent upon the collection of bytes, collection of bits. So you have to look at the pattern that's before you, okay? So let's put this together. All right, I've got a term and I got a breakdown. So we know 1 bit is 1 digit. It's 1 binary digit. We call it a bit. 1 byte is 8 bits. A kilobyte is 1,000 bytes. And you got megabytes. That's 1,000,000 bytes. How about gigabytes? What would that be? Whew, that's a lot of bytes, isn't it? Yeah, All right, so we got 1 billion bytes. And here's terabits. And just imagine if I were teaching this, maybe in a couple of years, terabits, we'd have another level for us, or maybe even a couple more. So let me give you some practical uses of binary. These are going to be related to code. We already know binary is necessary for the computer itself, but how about in your code? Because you're probably wondering, why do I need to understand binary? Yes, I understand that the machine needs it, but why would I care if I'm a software programmer or developer or engineer? So let's go through some practical uses of binary. Let's imagine that this is operation number 1. I put a 1 in the bit if it's complete, or 0 in the bit if it's incomplete. And as it goes through each one of the operations, there's an individual bit in this pattern. So if this is a byte in binary, I wanted to see, okay, did each of these operations get complete? I can use a system here to be able to say that operation 3 was complete, 2 was complete, 1 was complete. Hey, 4 didn't complete. 5 completed, but not 6, 7, and 8. So that would give me the ability then to be able to track potentially what happened. I could use this in error tracking. I could also use it in parts tracking, system tracking, maybe what a viewer is doing as they're clicking through a series of operations, right? So if you've got a web page up and you're trying to understand, okay, the person clicks this and completes this task, and they do that and they complete that task, and so on and so forth. So looking at a business process, there are times when you need to track what's happening through the system. This is a very simplistic way to be able to track each of those operations. Let me give you another one. You'll see the pattern's very similar, right? But in this case, what we're doing is that when operation 4 completes, we're going to do a bit shift instead. So now I'm doing operation 5. Maybe I change the 1 instead of being an operation complete. Maybe it's in process. So I know then that this is where I'm at right now. I'm at operation 5. Again, this is a simplistic way to be able to track a process. Operation by operation by operation. I've used it for state tracking. I've used it for inventory systems. I've used it for RFID tracking systems. I've also used it, so if we say state tracking, that's a pretty broad definition. If I have a business system and I'm building an intranet for them or an extranet for them, and I'm looking at a process or an order taking system, maybe it's in e-commerce, and I want to be able to track that the order has done this step, then this step, then this step, then this step. This is a simplistic way of tracking that. So these are practical uses of using binary in bits. Let's do some takeaways here. The binary system is a base 2 or positional power of 2. 1 digit, right, is 1 bit. A bit, one single bit, is either 0 or 1. That's it. That's why it's base 2. A byte is 8 bits, and a byte can be a number set of 0 to 255, and that gives us 256 possible values. Computers use bytes. So what you do is you take a byte and you combine them together to make much larger bytes, whether it's kilobytes, terabytes, gigabytes, whatever. You put those together, and now you've increased your computing power.